write down a little bit more too. So we're going to be graphing rational functions, and these are essentially my 6 steps. Step 1, you find the y-intercept. Step 2, you find the x-intercept. Step 3, you find the vertical asymptote. Step 4 is find the horizontal asymptote. Step 5, you plot everything that you did in steps 1 through 4. And then step 6, you plot even more. You plot some additional points to complete the graph. Namely, you plot additional points surrounding the vertical asymptote. Okay. So when you have to find the y-intercept, these are just some ideas that you learned earlier on in pre-calc. To find the y-intercept, you let x equals to 0, and then you solve for y. But there's a nice pattern to this. It flows nicely. Now, when you want to find the x-intercept, technically you do the opposite now. You say let y equals 0 and solve for x. But because we're going to have a rational function, the shortcut to this is you solve or let the you set the numerator n equal to 0, solve for x. The reason for this, just quickly showing you, is that if you have let's do this aside here on the bottom. If you have n over d is equal to 0, and you want to solve for x, one of the things that you could have learned, or you learned, was to write 0 as 0 over 1 and cross multiply. So n times 1 is n, and d times 0 is 0. So that's why that's the shortcut. To find the x-intercept, all you got to do for a rational function is just set the numerator equal to 0 and solve for x. Now, if you want to find the vertical asymptote, you set d equals to 0 and you solve for x. Right? So when you set the numerator equal to 0, you got the x-intercept. But for your vertical asymptote, you set the denominator equal to 0, solve for x. But be careful, because when you want to find vertical asymptotes, you just got to make sure that there's no common factors. All right, and to find the horizontal asymptote, you compare the degree of n and the degree of d, which we did in the previous example, right? Okay, so let's look at 2 examples, and I'll show you how this is being done. So here's example 1. Let's say we have the function f of x is equal to 2x squared over x squared minus 4. 2x squared over x squared minus 4. All right. In this example, we're going to apply my 6-step process. Okay. For your step number 1, you have to find the y-intercept. To find the y-intercept, all you have to do is set the numerator, set x equals to 0 and solve for x. So for your y-in, we're computing essentially f of 0. So this means that you have 2 times 0 squared over 0 squared minus 4. All right, let's do the arithmetic. What's 0 squared times 2? 0. Now, 0 squared minus 4 is not 0, negative 4. However, if you do 0 divided by negative 4, what do you get? Now you get 0. So my y-intercept as an ordered pair is just simply 0, 0. And I'm going to put a star on this. Okay, y-intercept is done. Next, we get the x-intercept. To get the x-intercept, now you set the numerator equals to 0 and solve for x. Your numerator was defined as 2x squared, so you set that equal to 0. Now, if you solve for x here, you have to do 2 things. You divide by 2, and then you take the square root on both sides. What's 0 divided by 2? 0, so we're going to get x squared is equal to 0. Now, if you solve for x by using the square root on both sides, x is equal to what value? 0. So as an ordered pair, the x in is just the origin, which makes kind of sense because if the y-intercept is the origin, then the x-intercept is also going to be the origin, 0, 0. All right, so we have the y in, we have the x in. Now we're going to get the vertical and horizontal asymptote. Now for the vertical asymptote, the first thing is that you want to look at your function and make sure that there's no common factors, right? So if I were to rewrite my numerator using factor form here, 2x squared over x squared minus 4, the numerator is already in factor form. This is just a single term, it's 2x squared. But if you look at the denominator, x squared minus 4 can be factored. X squared minus 4 factors as what? X minus 2 and x plus 2. Now, are there any common factors between the numerator and denominator? No. So there's no common factors here. So since there's no common factors, your vertical asymptote is simply the denominator. When you set it equal to 0 and solve for x, those are going to give you your vertical asymptotes, right? So here we'll have x minus 2 is equal to 0 and x plus 2 is equal to 0. In the first case, you got x equals 2. In the second case, you got x equals negative 2. Both of these values are my vertical asymptotes. Next, yeah. All right. Any questions? All right. Now we got to find the horizontal asymptote. So for the horizontal asymptote, just remember you have to compare the degrees of the numerator and the denominator. So the function f of x, again, was defined. Here you don't need to use the factor form. You could go back to the original form. Is defined as 2x squared over x squared minus 4. What is the degree of our numerator and what is the degree of our denominator? Let me just pull in that note. Degree of my numerator. 2. Degree of my denominator. What do I know about the degrees? That is the what? They are the highest power, but when you compare both n and d here, what do you see? What do you recognize? That they're equal. Very good. So because they're equal to each other, the horizontal asymptote is defined as y equals the ratio of those powers' leading coefficients. So what is the leading coefficient of the numerator? 2. What about the denominator? 1. So you get y equals 2. That's your horizontal asymptote. All right, now we have everything that we need to plot, basically. So I'm going to zoom out so that way I could show you what I'm plotting. I might have to go down a little bit more. All right, here we go. So here's my y-axis. Let's say here's my x-axis. Now we're plotting the origin. So that's a point on the graph. We have vertical asymptotes. There's 2 of them, x equals negative 2 and x equals 2. For the vertical asymptotes, please note that we plot them using dotted lines. Okay, we use dotted lines to indicate that the curves of the function does not go through or touches the curve does not touch or goes through those lines. So let's say here's your -2. Let's say here's my +2. And again, I'm drawing these dotted lines. Here we go. All right. We have a horizontal asymptote, which is y equals 2. So we're drawing a horizontal line. Now for the horizontal line, let's say, my bad. Let's say here's 1. Let's say here's 2. At y equals 2, you can draw your horizontal line. But note that you don't need dotted lines. The horizontal asymptote only indicates what happens as x approaches -infinity and x approaches +infinity, right? Informally, far left versus far right. All right, the first 4 steps are already plotted for us. Now we got to choose some additional points. Here's how we choose the additional points. For each vertical asymptote that I have here on my graph, I'm going to choose a test point to its left and to its right. Okay? So for example, if x equals -2 is my vertical asymptote, then I can choose x equals -3, and I can choose x equals -1. If x equals 2 was my second vertical asymptote, then I could choose x equals 1 and x equals +3. I plug them into my function, and I'm going to see what happens. All right. So the function was f of x equals 2x squared over x squared minus 1. So we're going to have to compute f of -3. Say again? -4? Oh, my bad. My apologies. So we have to compute f of -3, which is the same thing as saying 2 times -3 squared over -3 squared minus 4. Now let's try to work out this arithmetic. What is what is -3 squared? 9. 9 times 2? 18. So the top is equal to 18. Now let's look at the bottom. The bottom is -3 squared, which we know is 9. And then 9 minus 4 is 5. So you get 18 over 5. Now look at this fraction, 18 over 5, by the way. Is 18 over 5 is 18 over 5 greater than or less than 2? It's definitely greater than. The reason why I'm asking you that if it's nope, -3 squared is 9. 9 times 2 is 18. In the denominator, you have -3 squared, which is 9. 9 minus 4 is. Say again? No, there's no mistake here. It's good. Sure. Yeah, it's 18 over 5. I said 8. Oh, because I put. Oh, it was just a little glitch. No biggie. I changed it. We're good. So you have 2 times -3. Oh, sorry, -3 squared, which is 9. 9 times 2 is 18. You're good. And the reason why I'm asking you whether or not if this fraction was greater than 2 is all I really care about is if my test point was above or below the horizontal asymptote. And it is, right? This fraction 18 over 5 is like 3.6. So if this was x equals 3, then it's even bigger than 3. So it's somewhere here. All I care about is that it's above the horizontal asymptote at this point. All right. Well, I plugged in -3. What happens when I plug in +3? Will we get the same value? Yeah, because -3 squared and +3 squared are both 9. Then you will still get 18 over 5. which is still greater than 2. So, you get this point here again. So now I just got to plug in my other two test points, -1 and 1. And all I really need to do is just one of them. F of -1 is going to be 2 times -1 squared over -1 squared minus 4. What is -1 squared? So the numerator is 1 times 2, which is 2. Now, -1 squared is still 1, but 1 minus 4 is positive or negative? Negative. So we get -2/3, which, by the way, is less than the horizontal asymptote, which is less than 2. It's definitely going to be below the horizontal asymptote. So you have 2 is 2 over -3. All right. So 2 over -3 is a number that's bigger than -1. So let's say if here's -1, then you get this point somewhere here. All right. Well, what happens when I plug in +1? Will we still get the same value? -2/3? Yes, we will. The function was 2x squared over x squared minus 4. So 1 squared is 1. 1 times 2 is 2. 1 squared is 1. 1 minus 4 is still -3, which also is still below the x-axis. So you get this point. All right, so let me just clean this up a little bit. It looks a little sloppy. What I'll do is I'll change the font size. So we have this point here, and we have this point here. All right, we have everything now that we need to make our graph. The way that this works is as follows. Look at the very first point to the very left. We had -3, 18/5. That was the y value, right? If you notice, that point is trapped between both the horizontal and vertical asymptote. It's trapped there. By the definition of the vertical asymptote, I know that it gets really close to it, but it will never touch. It never intersects. It just gets really close. It's like that one annoying younger brother or sister that you have that waves their face in front of you and they're like, I'm not touching you, I'm not touching you. That's basically what's happening with this curve. It gets really close to that asymptote. So it looks something like this. Now, what happens with the rest of the graph? Well, by the definition of horizontal asymptote, it gives you the end behavior. That means that as the x values are approaching -infinity, the y values, the output values, they have to get closer and closer to your red line. Doesn't mean that it touches it, but it gets closer and closer to it. So here's like one piece of your curve. Let me do it again from the far right this time. When we had the point 3, 18/5, right? That particular point. What do I know? Well, by the definition of the vertical asymptote, it has to get really close. The curve has to get really close to that vertical line. So it's going to increase, but never touches. Now, by the definition of your horizontal asymptote, I have to get closer and closer to the line shown in red. Are we going to touch this line? Not really. The end behavior only says that we get close to it. We're getting really, really close. So we have 2 pieces of our graph done. All right, let's look at the middle piece now. I'm going to zoom in, and then I'll show you the full-blown graph. So we had 3 points. We had -1, comma 2/3, -2/3. We had +1, comma 2/3, and we had the origin. Now think about it. What do you think this shape is going to look like when I connect those 3 points? It looks like an upside down parabola. There you go. So we're going to have this. You could have plugged in more points to see that this is true. But overall, this is what your graph is going to look like. All right. And that's how you complete this problem in a 7-step process.